Thank you very much, Steve. So it's really a pleasure to be here. I really thank the organizers for bringing me to give a talk. I am enjoying very much the setting also. It's really nice. I will be talking about quantum spin liquids and superconductivity in honeycomb materials. So the work is a collaboration with a PhD student in Madrid, and a-Ruclz, who is at NEL Institute, and also Ben Powell, who comes from the organic community, and he's at Queensland. Okay, so there you can find some of the papers. So this is some work that we have been doing during the last, let's say, 6 years or so. So the motivation, in a broader sense, is understanding unconventional superconductivity in strongly correlated to the materials. This is a bit like the common thread of, well, I would say of all this, but the two main topics I will be discussing, one is related to this, is novel chiral quantum spin liquids in honeycomb Kitaev magnets, which is of course strongly related to Takagi's talk. So, and then I'll talk about unconventional superconductivity in some, well, they are really decorated honeycomb materials. And well, I will finish with some conclusions. Okay, so I think by now we have many examples of strongly correlated 2D materials or quasi 2D materials. So starting with the cuprates, of course, the organics, and more lately, well, we have the example of the twisted bilayer graphene, right? A common aspect, I would say, from all many of these systems is that you have the physics of the Mott insulator is present, and all these systems are they have different constituents, and so one of the questions is, what is the role of the Mott insulating phase and the mechanism underlying the superconductivity? Then, of course, the connection in a more specific, let's say, way of Mott insulating quantum spin liquid and superconductivity, which would be, I guess, the example of the kappa cyanide, where the Mott insulating phase is a spin liquid. And okay, so with the discovery of the twisted bilayer graphene, there's also the question of the role of flat bands and Dirac points on the electronic properties and the superconductivity on the systems. So this would be a bit like the overall, let's say, interest or motivation. So as already Takagi has introduced, I think a key idea in strongly correlated superconductivity is Anderson's RBB theory, which started from, well, his first proposal in 1973, that the Heisenberg model on a triangular lattice would be an RBB state. Though I draw a square lattice, but okay, this is the covering with the divers of the lattice, and well, a linear combination of all these would be an RBB state, and this would be a picture of an RBB insulator. Even though that in the triangular lattice, we know that the Heisenberg model would have an 120 degrees state. So even though this was not the case, the idea has been, of course, very, very important for the search of quantum spin liquids. But then after the discovery of the high TC cuprates, then he proposed that under fold doping, the system would, this RBB state would become metallic. It would be a high TC superconductor. And the wave function would be described by this projected RBB state, which has the holes, the doped holes together with a coherent superposition of the singlets in a superconducting state. So, okay, so since this since these ideas, the search of quantum spin liquids have been, of course, very intense. And also, as Takagi has also introduced, there are certain ingredients, right, that are important for finding quantum spin liquids. You need, or it's favorable to have small spins, and then either geometrical frustration or a strong spin-orbit coupling. Since the strong spin-orbit coupling can generate a quantum compass interaction, as the Kitaev model that has been discussed so intensively before. And here I'll, yeah, okay. And so we have examples of geometrical frustration, such as the kappa cyanide, which is the spin 1/2 triangular lattice, as a candidate spin liquid material, or the spin 1/2 Kagome lattice, like given by this inorganic system. So these will be examples of geometrical frustration in 2D, which may host a spin liquid, right? And in the case of the honeycomb lattice that was just introduced, the alpha ruthenium chlorine, we effectively have total J equal to 1/2 on a honeycomb lattice, and the interactions due to the spin-orbit coupling are behind the formation of the spin liquid, because we have a strong frustration of the spin ordering. So in this talk, I will concentrate on honeycomb materials and honeycomb lattices, and I'll discuss, well, or I will, let's say, address the question of whether we can have a novel chiral quantum spin liquid in a Kitaev magnet. So we'll be looking at this system. And the second part, I'll discuss another material or another system, which is this rubidium TT2H2, which is a honeycomb molecular system. And I address the question whether in this system we may have a quantum spin liquid, and whether we could see we could find superconductivity in this system by doping this. So this material is not much well known in the organic. Well, it has been recently synthesized. So, but I think it's very interesting, but we don't have much experiments yet. Okay. Okay, so getting then to the first part, this novel chiral quantum spin liquids in Kitaev magnets. So I'll make contact with the previous talk quite briefly. So we are then discussing this alpha ruthenium chlorine, which well, is supposed to have a Kitaev model or some aspects of the Kitaev model, let's say. And yeah, it has been found that, as it has been discussed very intensively before, that under a magnetic field, there's this half integral quantized plateau, although it's very controversial, as we have seen. But this, well, this sort of says that we may have a Kitaev spin liquid in this material under magnetic fields. Okay, so in order to introduce, so, yeah, okay, so the type of states that I'm going to discuss here are going to be, I have called them novel because they are, let's say, beyond the Kitaev solution. So I am, or we have been interested in seeing what happens when we add some other ingredients to the Kitaev model, and how the Kitaev spin liquid would be modified by these other contributions, and whether we may have some other type of quantum spin liquid. Okay, so so in order to do this, I need to at least revise very briefly the Kitaev spin model. So it's basically, well, as you have seen before, it's a model in which you have a bond-dependent exchange interactions. So in the honeycomb lattice, you have either X, Y, or Z Ising interactions. And this turned out to have an exact ground state, as Kitaev showed. And this is a spin liquid. And essentially in the region which I will be mostly discussing, which is this region of parameters, the three interactions are nearly isotropic. So I will be basically referring to this region where there is a gapless spin liquid with these Majorana fermion excitations and the Dirac cones. So the exact solution to this model, just briefly, can be obtained by just mapping the spins into 4 Majoranas in each side. And this is, well, one can divide these Majoranas on bond and matter Majorana fermions. And the bonds Majorana are called like this because they form a bond with the nearest neighbors. And so the spin operators can be written in this way, and they will recover the original spin Hilbert space. And by this transformation, then the Hamiltonian can be written in this way, where it's nearly quadratic, but you have this operator, which is a bond operator, which is a product of these two bond Majoranas, right? And so because this operator commute with the Hamiltonian, then these are good quantum numbers, and we can replace the Hamiltonian, these operators, by the eigenstates of this bond operator, and in that way we recover really we have a quadratic Hamiltonian that is straightforward to diagonalize by fixing these C2 gauge fields. Okay, so by doing that, then Kitaev found this spinless quantum spin liquid, which has 2 Dirac cones. Okay. And so under a magnetic field, as also was shown by Takagi, we get that the weak magnetic field on the Kitaev model essentially leads to a next nearest neighbor interaction, which has a flux, basically. And this opens a gap in the spectra of the Kitaev model, and this has an associated Chern number of plus minus 1, so it's a topological quantum spin liquid, or gap quantum spin liquid. And because of this, we have an edge state, a Majorana edge state, which has which leads to a half quantized thermal conductivity, which is what which we have been seeing before, and this is which has been discussed. And okay, so so if now we go beyond this Kitaev model, this was the analysis we have been doing, then there's no exact solution, and so what we have considered is to introduce a magnetic field, but in contrast to the solution by Kitaev, we don't restrict the magnetic field to small values, so it's not perturbation theory. So we want to go to moderate to large values of the magnetic field, and also we have considered Jaroszynski-Morilla interaction, and just to see what one can find from this, no? And essentially, because the first thing one could do is to a decoupling of the spins, and this decoupling is performed on the Majoranas, right? So it's a sort of Majorana mean-free theory, what we have been implementing. And so this has a magnetic spin liquid channel, and doing this this factorization together with certain constraints that bring the system or the Hilbert space of the Majoranas into the spin Hilbert space, well, one can find, let's say, solutions to these equations and discuss the effect of both the magnetic field and the Jaroszewski-Mori terms. So the model is a bit, yeah, sorry. So you mean the ansatz? Because well, we have basically tried a random sort of configuration, and then to the set consistency. So it's not biased in that way. But then we also chose, let's say, some good guesses of. But in principle, we didn't really. Right. Yeah. Yes, these constraints are satisfied on average. Yeah, that's correct. Yeah. Yes, the second neighbors, and it's only in the direction on the Z component. So it's in the D vector is in the Z direction. Yeah, you have some counting, but yeah, I don't remember exactly how it would be. Yeah. That's a good question. Yeah, but the DM, of course, is not realistic in terms of the material. It's a bit like a toy model, just to sort of see what are the effects of these two terms, right? Yeah. Right. No, the D is in the Z direction. Yes. We are preserving inversions. Yeah. So this would be the well, this would be the solution of just the Kitaev model using this mean field. It just recovers what we know. So it's a bit like just the dispersion relations of the Kitaev model, where you have the Dirac cones for the itinerant Majoranas, and then there's this small flux gap when you excite the fluxes of on the lattice, right? So yeah, so if we just treat first the magnetic field acting on the Kitaev model, so we now just add this. The main results are this. So this would be how the gap, this would be magnetization and the Chern number behave as a function of the magnetic field. And so essentially we open the Kitaev gap. So this is perturbation. This is consistent with the perturbation theory. But then as the magnetic field keeps increasing, then there is a change in the relation. So it doesn't go like field cube. So it's linear. And then it's suppressed until this point, this critical value where the system has a topological transition where you see the Chern number changes from 1 to -2. Okay. So sorry? That's in terms of the Kitaev K. That's right. Yeah. So yeah, and so then we will reach the gap polarized phase, which is non-topological, so it's trivial in that sense. So yeah, the main result then is that we find this intermediate phase as a function of the field in this region here between the let's say the Kitaev capped phase and the polarized phase. Okay. So in terms of the spectra, in this region, we essentially have a dispersion which is very similar to the dispersion of the Kitaev model, with a small gap at the Dirac points. Well, the gap was like this. And then this gap is increased until, well, it closes here. at the endpoints, and then we have the transition to this intermediate phase. So if one, let's say, introduces both the magnetic field and the Jaruzelski-Morilla in this ternary plot, we have the 3 parameters. Well, we would, at this point, we will be in the ungapped Kitaev quantum spin liquid. As we increase the magnetic field, the Jaruzelski-Morilla, we could also, well, we also found that there is an opening of a gap, but for a quite large value of this. And then in this direction, so this would be when we increase the magnetic field, we are in this intermediate phase I showed before, but all this region, let's say it has a finite region where it is stable in this phase diagram. Okay, and this would be the limit of the fully polarized phase. Okay, so this is the two, let's say, topological spin liquid states, which are beyond the Kitaev or different from the exact Kitaev spin liquid phase. Now, in order to have a bit of a test of this Majorana field theory, we compared with exact diagonalization on this model, and these are the spectra of excitations of the system as a function of the Jaruzelski-Morilla, so for different Jaruzelski-Morilla interactions, and this is the, let's say, the spectra as a function of the magnetic field. So what this is telling us is that yes, consistent with the Majorana mean field theory, there is something going on in between the Kitaev quantum spin liquid and the polarized phase. And in this intermediate region here, the spectra is, well, it's forming nearly a continuum of states, but it's suggesting that really there is an intermediate phase there. And this is actually consistent with other people's work. Hike and Trebst also find an intermediate phase for these values of the field, which are comparable to the Kitaev interaction. Okay, and this the other point is that with this Jaruzelski-Morilla, we find that although the gap is nearly 0 for Jaruzelski-Morilla for a small, or the gap is very small for no Jaruzelski-Morilla, as we increase it, we increase the gap in this intermediate phase. Okay. This is on 24 sites. This is in 18 sites, I think. Yeah. Yeah. So these people could go to, I think so. Yeah, it's a bit larger. Yeah. We did it on 18 sites. Yes. But I think it's quite consistent, the region where they find it, and also this compression of the states that is that occurs in the intermediate phase. So this is quite consistent. Yeah. Okay, so this, of course, if we could believe these experiments, which are highly controversial, then it would mean that there could be some integer instead of half integer. It would be an integer quantization in this intermediate phase, if this could be reached in some way. And okay, so this brings me to the second part of the talk. So I'll now switch gears and talk about these decorated honeycomb materials and the possibility of having a conventional superconductivity. So these materials, as I was saying, are less popular in the organic community because actually I became motivated by these systems by a chemist in Spain who was synthesizing these systems, and it's formed by layers of these molecules which have a triangular structure. So this is the molybdenum sulfur dimeth molecule, and they have as I say, a triangular structure, but they are arranged in a honeycomb lattice. And similarly, there is this rubidium TT 2H2, which also forms a honeycomb lattice. And this has been very recently synthesized. The common thing is that they are not really honeycomb, well, not only, let's say, honeycomb lattices. They have these triangles on each of the vertices of the honeycomb lattice. So it's really, we call it a decorated honeycomb lattice, okay? So this is the main building block of the system. So if you just do a naive tight binding model on this decorated honeycomb lattice, you would find that actually they are very interesting because they have Dirac points, they have flat bands. And so this, of course, also draw our attention. And because, of course, you may have non-trivial topology due to these Dirac points, and the flat bands are, of course, very interesting. If you put the Coulomb interaction, you expect to have strong correlation effects, right? So it's in some ways similar to the twisted bilayer graphene. Okay, so right, so we studied just a Hubbard model to introduce the Coulomb interaction effects on this system. So we have an intra-triangular hopping, we have an inter-triangular hopping, and an on-site Coulomb with a minimal model. And if we go to a limit of very large U, then this model would map into a Heisenberg model. And so I return to the questions that I had at the beginning, just if you have got lost. So the first question is whether the ground state of the Heisenberg model on this lattice is a quantum spin liquid. This is the first question. And then what happens when we dope this system? So the question we had in mind was whether superconductivity would rise. There are, of course, many other aspects, like what is the role played by the flat bands, the Dirac cones, and so on, that well, I won't discuss. So regarding the first question, whether there is an RBB or a spin liquid on the decorated honeycomb lattice, so we have relied on previous works on the literature. So there are tensor network calculations at zero temperature, which in principle, they show that there is some dimer valence bond. Okay, valence bond solid, right? And okay, there is a spin gap in the system. So, but these calculations indicate that there is a suppressed magnetic moment. So really, it's a disorder, a spin disordered system. Actually, with some analysis on small clusters, we could see that the overlap with a spin liquid ground state is of the exact solution with comparing with the RBB state is the overlap is nearly 1. So, and the spin correlations are in very good agreement with large size calculations. So this nearest neighbor RBB state seems to be a very good candidate for describing the magnetic properties of this lattice. So, well, starting from an RBB state, then we basically based our analysis on following a bit the Anderson idea that we could have RBB superconductivity here. And basically, we did an RBB decoupling of the TJ model and basically map out the phase diagram of the system. So, and the main result is this one. So we have that there is, as a function of the doping and temperature doping, so there is a region around here where we have different types of superconducting states ranging from extended S extended D, and the most, let's say, unconventional is this F-wave singlet pairing, which, okay. At the beginning. Okay, I'm going to show now the real space configurations of this. But for us, what was really, of course, when one says it's F-wave, normally one thinks in triplet, right? Of course, that would be the. But this is actually allowed by the lattice. Okay, so the fact that we have a decorated lattice, by just looking at the superconducting states in this system, one finds that really, well, you can have the F, the S, and this would be the extended D, which would look in real space like this. You have this alternation, and it would correspond to the C2 configuration on the group theory of the lattice. So the pattern would be could be any combination of these two in some way, right? So so the main new thing on this lattice compared to the honeycomb lattice is that we can have, due to this decoration, we can have other possible unconventional states like this F-wave singlet, which is allowed by this unit cell, which is much larger than the one you would have in the honeycomb lattice. And well, this we could understand, of course, within our theory, the different pairing states that we are finding by looking at the gap equation and looking at the different, let's say, eigenstates of the system, pairing states of the system. And because the coupling in this RBB theory has the projection, has this, you are projecting out the W occupied sites, then the effective coupling is really increasing with lowering doping, and we can go through all these different solutions. So it's just, yeah, and so we can go from the star to the F as I showed in the phase diagram. And this is again consistent with some hexagonalization in the half-fill system. We find that really the extended S at half filling is consistent with this RBB theory. And yeah, and so this brings me to the conclusions that, the main conclusions are that we have that the Kitaev magnets and their magnetic fields or the DM can really lead to some novel chiral quantum spin liquid, as I showed. The RBB quantum spin liquid seems to be a candidate for the ground state of the Heisenberg model on the decorated honeycomb lattice. And this would be relevant to these materials I was showing, the molybdenum and the rubidium molecular crystals. And then you could find, well, we found superconductivity within this theory under Hall doping. Okay, so with this I'll finish. So thank you very much.